Alright, let's get started with Lesson 3, Water. Now, as we talked about earlier, water has a very unique ability to act as both an acid and a base. In other words, it can either donate a proton or accept a proton in that idea. Because of this, water can basically auto-ionize, which essentially what it means is because water has the ability to act as a Bronsted-Lowry acid or a Bronsted-Lowry base, this can result in water molecules transferring a proton from one water molecule to another water molecule. So in case of like this, we have water, H2O can actually transfer a hydrogen ion or a proton to another water molecule, which is going to act as the base. Essentially what we're just saying is water can react with itself. And so in this case, we have the acid and water, the base. All right. In the result of this, we form the hydronium ion and the hydroxide ion every time when water reacts with itself. So if you take a glass of water, for instance, and all it is pure water and nothing else in it, then essentially the water molecules will react with each other, one water molecule acting as an acid and the other acting as a base, and in the result we form the conjugate acid, which is the hydronium ion, and the conjugate base, which is the hydroxide ion. And you can see from our model here, water, in this case, this one is the base because it's accepting the proton. This is the acid, and we form our conjugate acid and our conjugate base, the hydronium and the hydroxide ion. And that is what is known as the autoionization of water. Very important for you to understand. Alright, so in the result of this, in fact, is when we draw this equation one more time, because it's really important. So water plus water reacts, and it's going to form an equilibrium. Let me draw a better arrow here. It's going to form an equilibrium with its conjugate acid and base, the hydronium ion and the hydroxide ion. Okay, now these ions are going to be aqueous, and the water, of course, is in the liquid state. So when we write out the equilibrium expression for this, we would write Kc is equal to the hydronium ion plus the hydroxide ion. Now, we cannot include the waters because they're in the liquid state. And remember, in the equilibrium expression, we cannot include liquids. Now, we're going to change the Kc value to what is known as the ion product constant, Kw. W for water. Kw is the same as Kc, so Kw is equal to Kc. It just refers to the fact that we're talking about the equilibrium expression for the autoionization of water. And so we'll use Kw instead. Now, this Kw, of course, just like any Kc, Ka, Kb, Kw is temperature dependent. And so Kw here is going to be written at 25 degrees C, and that's important for you to note. Now, it turns out that Kw at 25 degrees C is 1.0 times 10 to the minus 14. Very super small. That tells us a lot about the equilibrium position here. It tells us that the equilibrium position lies to the left, and it's going to be water favored instead of product favored. So in other words, when we have a glass of water, most of it is going to be H2O. Very little of it reacts with each other to form the hydronium ion and the hydroxide ion. So we would assume that the hydronium ion and the hydroxide ion concentration at equilibrium would be extremely small in the presence of liquid water. All right? So Again, let's just relook at this really quickly. I have a glass of water. Most of the water is going to be in its H2O form because the equilibrium lies to the left. The Kw is so small that very little product is going to be formed when water reacts with itself to form the hydronium ion and the hydroxide ion concentration. Now, the Kw value at 25 degrees C, you need to memorize. You need to have this down quite well. Okay, so memorize it. All right, now we can use this to determine the hydrogen ion concentration, the H plus concentration at equilibrium. So what I want you to remember this is when water reacts with water, it forms the hydronium ion plus the OH minus. Now we can make this simplified and we can just say that water reacts with itself and so it breaks down to form H plus OH minuses. So essentially the hydronium ion and the H plus we can consider being the same thing. And so often we're going to just use H plus instead of the hydronium ion. So from here on out, the hydronium ion and an H plus are going to equal the same thing. They're going to mean the same thing, okay? It's just that we're making it the equation a little simple. All right? So let's go back to drawing our idea here of H2O breaks down into our hydrogen ion plus our hydroxide. And remember, really, this is really the hydronium ion. We're just simplifying it. Okay? So that means that Kw, we said, was 1.0 times 10 to the minus 14. Okay? So if we plug this equation into our equilibrium expression, so our hydronium ion times to the negative 14 is equal to the hydronium ion concentration times the hydroxide ion concentration. Okay? Now, if we were to actually erase this and make this an X value, because we really don't know what that concentration is, nor do we know the hydroxide ion concentration. All right? But we're going to assume that they're equal to each other because we know that the ratio is 1 to 1 to 1. Okay, so we have a 1 to 1 ratio there. So we have x and x. So that means essentially is 1.0 times 10 to the minus 14th equals x squared. So if we take the square root of both sides, we should get an x value of 1.0 times 10 to the minus 7. All right? So what does that tell us? Well, let me erase all of this so I have more room. Hopefully you have more room in your notes. That tells us that the hydronium ion concentration, which is really equal to the H plus concentration, because they're the same, is equal to 1.0 times 10 to the minus 7 molar. All right? And the OH minus concentration is equal to 1.0 times 10 to the minus 7th molar as well. So both concentrations at equilibrium are going to be equal to each other. The acid and base concentration, in other words, the hydronium ion, which is the acid, and the hydroxide ion, which is the base concentration, are equal or equivalent when water reacts with itself. All right, so those are pretty important values to make note of in this idea. Also, what it's really saying is that using this relationship of Kw and the equilibrium expression for Kw, we can determine the H plus concentration, or we can determine the OH minus concentration of a solution. All right, so we got some couple of beakers here, and they're full of, one is an acid, which is HCl, one is just water, and one is a base, sodium hydroxide. So in terms of relatively thinking here, the hydronium ion concentration in this beaker should be greater than the hydroxide ion concentration. All right. When we think of this, the acid concentration in hydroxide, since it's a strong acid, should be much higher than the hydroxide ion concentration with water reacting with itself. All right. And the plain water, we should have the hydronium ion concentration should equal the hydroxide ion concentration. Let me make these smaller so I have more room. Hydronium ion concentration is greater than the OH minus. And then for water, the hydronium ion concentration is going to equal to the hydroxide concentration because it's just pure water. And then for the base, we should have a hydronium ion concentration that's less than the hydroxide ion concentration. Running out of room there, okay? So those relationships are very important. Always in a acid, when we have an acid that we added to water, the hydronium ion concentration is always going to be greater than the OH minus concentration. When we have a base and we add the base to water, the hydroxide ion concentration is always going to be greater than the hydronium ion concentration. So we can look then for aqueous solutions. Remember, so aqueous means water, or substances dissolved in water, so our acid or base. Then the concentrations of the H plus and the OH minus are going to be inversely proportional to each other in those situations. All right? So now, knowing all of this, we can basically calculate the H plus concentration or the OH minus concentration in an aqueous solution if we know one or the other by using the equilibrium expression Kw. So Kw is equal to the H plus concentration times the OH minus. Remember, the H plus is just the hydronium ion. So if we know Kw, which is 1.0 times 10 to the minus 14th, and the H plus concentration we don't know, but we do know the OH minus concentration. Then the H plus concentration times the OH minus concentration. Oops, let me rewrite that as 0, 1, 0. Then by solving this equation, we should be able to figure out what the H plus concentration is, which in this case should be 1.0 times 10 to the minus 12 molar should be the H plus concentration. And again, we can do that using this equilibrium expression, okay? So here's another problem. One more problem. So Kw is equal to 1.0 times 10 to the minus 14. We know that. So if we plug in our hydroxide concentration, we should be able to find the H plus concentration of taking 1.0 times 10 to the minus 14 is equal to the H plus concentration times the hydroxide concentration. And that means the H plus concentration, once we solve for this, should be 5.6 times 10 to the minus 6 molar. And you should be able to verify that by doing the mathematics. All right? So this equation using Kw and the equilibrium expression for Kw is a nifty way to find either the H plus concentration, or we can reverse that and find the OH minus concentration in an aqueous solution. And it becomes very handy in this case. So just basically spend some time understanding the autoionization of water. Remember that water reacts with itself. It can be one water molecule acts as an acid and donates a proton to another water molecule, This forms the conjugate acid, the hydronium ion, and the conjugate base, the hydroxide ion. And so by knowing this, you can know the equilibrium expression for Kw, and therefore you can figure out how much hydroxide or hydrogen ion concentration there is in any aqueous solution adding an acid or a base to it, to water. Okay, so that's essentially it for this. I know, again, acids and bases, there's a lot here. It's complex. We're going to spend some more time with this in class. So come prepared with some good questions, and we'll go from there. Okay, so that's it for this lecture video.